In order to facilitate enterprise adoption and try to mitigate some of these risks, security solutions have been developed, such as secure containers, which claim to provide enterprise-grade security for Android devices. Because of this, there's an increasing need to be able to assess the security claims of such enterprise-class applications and their vendors. During this talk, we will walk you through many of the real-world threats and attack vectors those threats might use to try to obtain your data. More or less, we're now carrying very powerful portable devices which store extremely sensitive data. These devices are almost always on and almost always connected. They're not like laptops, which you use and you shut down, hopefully. We're constantly using these devices. They come with us everywhere, out to dinner, out drinking, on our trips, personal and work, even to the bathroom. They also constantly have a stream of data flowing in and out over cell networks, Wi-Fi, Bluetooth, etc. So many new pieces into this mix. With all that in mind, are data security models based off non-smartphones, standard wireless phones, really all that relevant? Also, lots of marketing claims are being made. What are they? What do they mean? How do they compare to threats and attack vectors? In other words, if your data is secured at rest, but it's never at rest, is it really that secure? Finally, we're going to explore a few techniques you can use to verify if you really are secure from the different threats and attack vectors. Before going much further, for those of you who don't have too much Android experience, I wanted to go over some basics that will help you understand some of the more technical information we'll go over later in this talk. Android at its core is an amalgamation of Linux and Java, with a little Google magic sprinkled in. As such, some of the same techniques used while auditing Linux and Java applications can be ported to Android, though with some modifications. Android applications, for the most part, are written in Java, but run within what's called the Dalvik virtual machine. Dalvik was designed to be able to run multiple applications and separate VMs concurrently, but it still relies on the Linux kernel for low-level memory management and threading. As a side note, Android does also support running native code, which usually is used in security or performance-sensitive applications. Android also, by design, attempts to do application sandboxing. Such sandboxes are set up based on privilege separation. Each application runs with its own identity, in other words, user ID and group ID. This was designed so applications, by default, don't have permissions to perform negative tasks that could affect other parts of the system. These aren't all that differences, but are some of the relevant ones to this talk. Enterprise class applications. Let's talk a little bit about Android in the enterprise. Android's currently focused towards the consumer market. It lacks reliable central management features, such as granular access control, security policies, device analytics, as well as the means to secure data at rest, such as full disk encryption. Android also lacks the ability to allow applications to easily encrypt their data in a way that would keep it secure from rogue applications such as spyware or malware. More or less right now, Android has a very limited set of features that would help keep it secure in the enterprise. Android 3.0 is changing some of that. It's implementing some more enterprise-type features such as full disk encryption, remote password reset, and a few other features. Though Android 3 isn't being released for smartphones, and some of these features might land up in Android ice cream sandwich. Let's talk a little bit about what the mail situation looks like. Android currently relies on ActiveSync for any kind of enterprise mail. Unfortunately for us, ActiveSync comes with a whole set of its own issues. By default, has a very limited set of security features, and the features it does have are not always the most supported or stable. It also relies on the Android certificate store for SSL verification, which may not always be the most up-to-date. Aside from how ActiveSync sends information over the air, we should look at how data is stored on the device. It currently relies purely on the Android security boundaries and the choices of the users to protect the data. In other words, the data is completely unencrypted. Okay. Due to these security gaps, we've seen an emergence of what are called enterprise-class applications. These applications attempt in multiple ways to improve the security and manageability of devices. They provide the ability to do remote analytics, remote wipe, password management, application whitelisting and blacklisting, as well, in some cases, as credential offloading. Communications are usually handled by SSL to and from the server. A lot of these features have been taken from BlackBerry Enterprise Server, which has more or less been the gold standard of enterprise mail for a long time. Good or bad, BlackBerry does have tight software and hardware integration. This allows them to build their software and security with ties directly to the hardware. Though we are seeing certain enterprise-class vendors working directly with the hardware vendors to improve integration. Now on to secure containers. Secure containers attempt to provide data segregation. They encrypt enterprise mail, contacts, calendar, some files maybe on the device in order to keep it separate from your personal data. These containers usually rely on a PIN that's separate from the standard enterprise Android PIN. Let's talk a little bit about the marketing claims made by some of these companies. First one I found very interesting. Governments have tested the product and approved it for their most sensitive deployments. Kind of scary. Potentially top secret information on these devices. Another one, several security conscious enterprises have approved the use after rigorous internal or third-party pen testing. Can we see these tests? How come this information isn't published? Finally, helps government agencies comply with DoD Directive 8100.2, Homeland Security Directive 12, and Federal Information Security Management Act. Let's talk a little bit about DoD Directive 81002. It was more or less written as guidelines to secure wireless devices. It was published in 2004. That was a whole 3 years before the first Android beta even showed up on the market. By now, this document is over 7 years old. I would think that threats and attack vectors in the last 7 years have changed a little bit. Well, this document's mostly needed for compliance. If it was used in the design of these applications, it's a little bit scary. Another security claim. Performs remote wipe of enterprise data. Again, this is a nice feature to have for a checkbox. This would help in this situation your device might be stolen. But I have a strong feeling that most sophisticated attackers would probably just stick your device in a Faraday cage or pull this in. Okay, some more marketing claims. Corporate data is highly secure. Highly secure from who? I think that's a big part of what this talk is about. At least personally, I'd like to know when someone is saying my sensitive corporate data is secure, who's it secure from? Is it a random phone thief or governments? Okay. Over-the-air transmissions and enterprise data at rest on the devices are secured with industry-leading AES 192. Cool. Nothing wrong with AES 192. But let's talk about the usage. Over-the-air transmissions. Is AES 192 used on its own, or are they relying on SSL? How is that configured? Who handles certificates? Now, onto the data. Whose here's phone is currently off? Raise your hand. Exactly. How often do you shut off your phone? Do you shut it off when you go to bed? I know I don't. How about when you're walking on the street? How about when you're at a hacker convention with some of the best hackers in the world? That's what I thought. Now let's talk a little bit about FIPS. What is FIPS? What's the FIPS module? Is there a little chip in there, or is it just some copy and paste code? The NIST, which is the National Institute Standards of Technology, issued the FIPS 140 publication series to coordinate requirements and standards for cryptographic modules that include both hardware and software components. So I want to talk a little bit about the different FIPS levels. Well, on a side note, most of the enterprise applications we've seen say they are FIPS 140-2 level 1 secure, whatever that means. Okay. FIPS level 1 more or less means at least one approved crypto algorithm is used by the application or the module, that the module is self-contained, and it's approved and reviewed software module. More or less, these modules have to correctly implement the crypto algorithms and shouldn't let others pass around actual key information. Callers should only have key handles. Level 2 should show evidence of tampering. 3, detect and respond to attempts at physical access. 4, detect fluctuations in environmental conditions. If the temperature rises around the device, potentially it'll shut off. Okay, now that we've talked a little bit about what the claims are, I want to talk about what the actual threats to your data are. Remember, these are applications that are meant for CEOs of enterprises, government agencies. These are not consumer applications. So the threats and who might be after your data might be a little different. First threat, a malicious hacker. Just the average hacker, maybe a little bit better. They mostly going over internet, probably won't have access to the phone itself, but can still be pretty powerful. The next one would be, say, corporate espionage. Competing company wants access to your data, maybe steal plans for missiles, things like that. They do have, most likely, highly technical resources and large financial resources. Now, government entities, they may be able to get access to your phone fairly often. Are you going through security when you travel? Do they stop you randomly? You don't know. They also may control the infrastructure you're using, from the cell phone networks to the wired networks. You name it, they may have control over it. They have large technical resources and large financial resources. Finally, your significant other. Chances are their technical and financial resources aren't all that high, but they may want to know what data you have on your device. Okay, let's see what they're after. They're after potentially emails, sensitive documents and files, credentials, text messages, contact lists, call logs, calendars. Say if you have any code or plans on your phone, you know which kind of sensitive data you have, so imagine that. Let's talk about where the data resides. Classify it mostly 3 areas. It'll be on the server, so your mail server, etc. It'll be in the air. Think about that. How much sensitive data is floating around in the air right now, all around you? And finally, it'll be on the device. 2 areas. One in the flash, NAND, or whatever, or RAM, if it's being accessed. Let's talk about how these threats might actually try to obtain the data. They might try to steal the device while it's powered on. This is one of the least sophisticated, but one of the most serious attacks. With the device that's on, we can not only access what's on the flash, but potentially the data that's stored in RAM. Let's look at some of the ways we can actually get the RAM contents. Maybe some ways through Android itself. Is USB debugging enabled? If it is, we can easily obtain root access through ADB using different exploits. What if it's not? Can we bypass the lock screen? As we've seen, multiple vulnerabilities have been found in it. Another area that's not talked about too much is cold boot attacks. Cold boot attacks on the mobile platform are extremely difficult to pull off and may require a lot of technical and financial resources. 2 potential ways of doing them would be a software or hardware-based attack. Software would require gaining root, rebooting the device, and trying to grep through memory, say flashing it, etc. Hardware would actually require you to pull off the chips or somehow read them while they're being accessed. Neither are very easy, but it is potential with enough financial resources. Another one to possibly think about is JTAG. A lot of your phones still have, or some of your phones still have a JTAG interface. Depending on the board configuration, they may allow debug access to RAM, though it's highly unlikely. Let's talk a little bit more about if the device can be protected in these circumstances. One of the relevant marketing claims to this is data is highly secure. So can your data be protected? In some circumstances. More or less, if nothing sensitive is in RAM when the device is stolen, your data could potentially be protected. How might you secure that? Sensitive data should immediately be zerotized when it's done within RAM. So another attack vector. The device is stolen while it's off. Only flash may be available. And the ways to get access to flash are pretty similar the ways to get access to RAM. You know, we could use the USB debugging or bypassing the lock screen, but we also have a couple other attack vectors we can use. There's some more practical ways to get to flash via hardware. You know, the actual reading of flash chips is a fair amount easier than reading RAM, but again, it's not that easy, and you know, you don't have to worry about data loss due to time. And another really interesting way is over USB. You know, certain companies are now releasing hardware devices that can read the flash directly over the USB port. You know, these devices are being sold publicly and have been shown to work in multiple cases. You know, the most popular is this UFED device. The latest version claims to support direct bit-by-bit copying, as well as the ability to bypass the lock screen. And the only thing, they're currently limited to certain Android devices, but that list is growing, and Samsung is supposedly next on that. Based on what we know, UFED has created different exploits to be able to do this. It's really cool stuff. Let's see. Now, with the device powered off, can the data be protected? You know, a relevant claim would be data is secure at rest. Well, I believe it can be protected. How might that be done? A strong password-based key derivation. Another would be a server-side key, meaning that the decryption key is actually kept on the server and has to be sent down every time you want to access the data. See, another interesting attack vector would be if someone borrows your device. More or less takes your device and returns it. When might this happen? Say while you're sleeping or passed out. If you're stopped at the border, you know, they can grab your device. We've seen that before, say Moxie, Marlin, Spike. Stop while driving, you know. Police pull you over. In the States, at least, certain states it's now legal to search your phone when you're pulled over while driving. And another thing, UFEDs are actually being heavily used by police now. Think about that. You get pulled over, and within 5 minutes, the police legally have a full copy of your device. You know, again, these are similar attack vectors as a stolen device, but some slight differences. One, it's time limited. Less likelihood of the chips being removed and attacked. But the difference is the device could come back to you modified. More or less, your attacker could install malware or backdoors that give them a very strong foothold into a persistent attack. You know, a backdoor on a sensitive device without the user knowing the wiser. You know, any information that comes on it after it's been returned, you know, may be stolen. You know, so say it is taken while you're sleeping. That could be potentially 100% covert, and you may never know. So can it be protected in this case? In some circumstances. One, nothing sensitive can be in RAM if the device is stolen while on, and the device can't be used afterwards. How might you potentially secure it? Again, sensitive information is to be zeroized. Full disk encryption should be used with a separate boot key. So if someone gets the device while it's off, they can't modify the data that's on there. And then tamper detection. Some companies are now trying to build in, if someone starts messing with the settings, enabling USB debugging, so on and so forth, that all the applications shut down. Another area to look at is network-based attacks. Man in the middle or passive interception. You know, some of the threats may actually have control of the cellular providers. You know, certain governments, so on and so forth, have full access to that. You know, then let's also look at cellular protocol vulnerabilities. There's been a lot of talk about that. Vulnerabilities in GSM, WiMAX, so on and so forth. Femtocell issues, you know, connecting to a femtocell. There's actually a talk on that, I think, a little later today. Can't wait to see that. Wi-Fi. A lot of phones still automatically connect to Wi-Fi access points around them. And finally, SSL. You know, if SSL is not configured correctly and certificate verification isn't done, easy to get in there. A couple more that are a little bit newer are baseband exploits, which could potentially give remote root access to these devices, as well as have the potential for a persistent backdoor on the device without it running an app code. Another interesting one is a firmware over-the-air update. If someone were to, say, bypass signature checks or do their own signing, this could cause major damage, and again, you could push a completely backdoored firmware. So can the data be protected in this case? And the relevant claims for this really are patented end-to-end security in AES 192. We believe the data could potentially be protected. How? Properly implement SSL to prevent most attacks. A big thing to also do is certificate fingerprinting. Don't rely entirely on external root CAs. You want to make sure those certificates are legit. Final kind of area we're going to look at is application-based attacks. Let's start with malware. Again, we're seeing lots of people downloading malware from the app markets. Even there's the potential of getting it from Android vulnerabilities, say browser or PDF based, maybe the mail. I'm going to break malware into two areas, userland and root. With userland, it's mostly contained within the standard Android security boundaries. With root, it can access flash and RAM. And then there's also the standard application vulnerabilities in enterprise class applications, permissions issues, buffer overflows if they're using a lot of native code, and just misconfigured settings. So can the data be protected? In the case of malware in the userland, I'd say yes. How? Application whitelisting and blacklisting could help. If you prevent the malware from getting on there in the first place, then you reduce the chances of actually having issues with your application. Another, which some of these enterprise class applications are looking at, is Granular Os Controls. Take more control of the OS and prevent certain calls from even succeeding. And finally, intent filtering. Do not allow anything to communicate with your application if it's doing any kind of sensitive work. What data can't be protected from? Anything that obtains higher level permissions in the secure container. So malware with root access, baseband exploits, and firmware over the air exploits. These are some really scary areas that have very few, if any, protections from. You're walking around, someone causes, baseband exploit, boom, all your sensitive data could be gone. Now that we've kind of gone over some of the different threats, attack vectors, how secure containers could do things, let's look at how to actually verify if they are. And with that, I'm going to turn it over to Mark to dive into the actual techniques you can use to verify the claims or to break enterprise class applications in secure containers. Mark?
Thank you, Matt.
Enter.
So now we are going to see how we can verify if we are protected with these applications. We are going to show techniques and tools we used to reverse engineer enterprise class applications and secure containers. We'll first determine how we can, what we expect to see in an application. We'll then show how to reverse engineer them with existing tools. And we will see the issues we were looking for when we did that. We'll talk about the Dalvik and native code part. We'll also show how to do structured and unstructured memory analysis. And we'll also show how we can modify an application as well as using dynamic analysis in order to audit it better. So how is an application organized? Each application is installed and compiled into one single file, an Android package, which is basically a zip compressed file. This APK contains several files. The manifest, which is an uncoded file which contains the application name, version author, allowed activity, and other permissions. It's mostly based on whitelist. There are some signature files that ensure data integrity of the package. So packages should not be modified without signing them with a developer's key. Well, except that applications are self-signed, so you can actually modify them and re-sign them with your own key. So there are also some resource files. Sometimes they are native libraries. The classes.dex file is the core of the package. It contains all the Dalvik VM bytecode. This single file contains all of the application classes, and this is one of the main difference with the Java VM machine, where class files are loaded as they are referenced at runtime. So our goal is to be able to fully understand what an application does. Those enterprise applications may have obfuscation, and mere reversing of an application with a single tool rendering Dalvik bytecode is not at most practical. So the idea is to understand the application flow in order to look for logic or design issues, but also specific issues related to encryption. Secure container is very specific, so that's why we wanted to have a real understanding of the flow of the application. So we'll start from the beginning. The Android SDK has a client that's allowed to connect to a server on the phone if debugging mode is enabled. So the app needs to be pulled off the phone and unzipped first. We want to convert the DEX file into more readable code. So there are several solutions to do that. Baxmali and Dedexer can decompile the file into simple assembly-like syntax, similar to Jasmine, but with Dalvik opcodes. So Jasmine is a syntax that had been created for describing JVM class in the first place. So we'll prefer Baxmali to Dedexer because the application can be recompiled using Smiley. A solution had also been developed to decompile the DEX file into a jar file, but there are usually a lot of inconsistency and error in the decompiled code. So here are some examples of Smiley code compared to the Java equivalent. So as you can see, we have one line of Java, which is very basic ternary operation, and we have like at least 10 lines of Smiley code. Well, it's readable, like the Smiley is like close to assembly, but there are lots of information, annotation, debug info, line info, but it's still way more painful than Java. So I know a lot of people in this room do not like Java. I'm not the biggest fan either, but you have to admit that Java is definitely more practical in our case if we want to understand the flow, the control flow better. So yeah, we are talking about analyzing very big applications here. So the less code we have to read, the better if we want to understand it. So our goal would be to read a code as close as Java as possible for now. So let's see how perform the tool I talked about, DEX to jar, regarding decompiling DEX files. So yeah, here an example of a pretty bad decompilation. So it's not obfuscation, this code doesn't mean anything, it's just an incorrect conversion, which leads us to the difficulty in converting DEX format into Java's format. So we're going to talk about the difference with the two formats. Classes written in Java are compiled into bytecode format, which is one big DEX file. Dalvik is also register-based, which leads us to having slightly different opcodes, but also LED total code. But the issues that concerns us regarding this decompiling issue are first of all that so we're going to talk about the JVM app structure first. In the Java VM format, Java classes replicate elements in constant pools within the multiple class files. These pools refers to method name, classes, and constants. The X compiler eliminates the replication. It creates a single pool and eliminates an inline constant value into the bytecode. So determining type is way more difficult since we have direct constant into the code. One of the other issues is that Java bytecode structure loosely mirrors source code, whereas Dalvik bytecode does not, making it way more difficult to reconvert into Java code. The other issue is that Dalvik types are ambiguous. Some opcodes are the same for integers and floats, which lead to very hard decompilations. So right, well, should you try to write your own decompiler and solve these issues, or maybe not? Maybe you want to have a bit of the two worlds, having like the advantages of Smiley using some Java decompiling parts from DEX to jar. So what we want to have here are some accuracy of the Smiley code and yeah, a big overview of the app using DEX to jar. So what we can do is to find inconsistent methods in Java decompiled code. They're usually pretty specific and can be spotted quickly. So here are some examples. I don't know if you can see. So it's mostly inconsistent code. But there are like a pretty precise pattern. When you see that kind of code, it's not obfuscation or anything. It's just a wrong decompilation. So in that case, you can manually convert those methods. Or you can do that as you read through the code and looking for specific issues. But yeah, so DEX to jar converts a lot of code. A good part of it is still readable and correct. But just when you see some specific pattern of inconsistent code, you can just replace it with Smiley code. Or, if the code is used a lot by the application, you can just convert it manually. We also use some visualization tool. So AndroGuard here use an APK to take an application, visualize the control flow of an application. As you can see, you have each, as you can see, the whole application, all the links within all the calls, function calls and everything, so it's way easier to read a control flow. So now we have the key in hand. Let's verify if we are protected. A secure container must provide a certain degree of protection. Depending on the scenario of attack we want to be protected from, we're going to look for different potential issues. First of all, the protection schema and encryption design. We are going to be looking at how the data is encrypted. And this information would allow us to determine how to do an attack on a phone that is off for our first step. Let's say they use AES, which is good, but what if they use a static key in the application? It would make the encryption kind of worthless, right? Same thing with retrieving the key with some static data on the device. Let's say the EMIE, for instance. What if they use very low entropy key, no IV or ECB mode? It's going to be easier to find the key. They could also derive the key. They could also derive the encryption key from a password using password-based key derivation, which is better, but what if they use a low number of iterations and you can just brute force the password using like a GPU cluster or a single GPU with your machine? Let's say also they don't use salts with a password or things related to password encryption or plain text password in files using obfuscation basically. So it's definitely, it wouldn't be a good thing and you could look for those issues. So there are definitely a large number of potential issues within encryption and the schema, the protection schema. So now we want to look at how cryptographic material are handled by the application. Let's say we have two valid case scenarios to protect the data at rest. The first scenario would be to derive the key from the user's password using password-based key derivation function with a very high amount of iteration and a rather complex password. That would be one of the problems with this implementation. And the second one, and maybe better but less practical, would be to have a server-side key protected with a pin and only a few tries allowing you to retrieve it. In those two scenarios, the question is, how long should this key be kept in memory and what are the attack scenarios? We would want to have our data protected when the phone is on and the screen locked. If they use FIPS modules and they retire the encryption key after use, this wouldn't be practical. They would need to the user would need to retype the password at for each request. So let's say the keys are retired only when the lock screen kicks in. That can be fine and protect your data if the phone is stolen. So it would be one of the things you would be looking for in a secure container. There are also some more specific things related to secure container you could be looking for. How is the password recovery function working? If they use password-based key derivation, how can you retrieve the key if you lose your password? How can you reset it without the key or the password? The specific key is supposed to be needed in order to decrypt the data. They would have to store your password or key server-side, or maybe they use something else that would allow you to retrieve or reset the password. Okay. Yeah. So you could also be looking for intent permission, some other issues. Are the intents accessible outside of the application? How much can you do with those? This should be an area where user and malware could play in, and it's a common vulnerability. So some more specific issue can be raised, like lock screen process. How do they lock the phone? Connection credentials, or if they use a key store, like a hard-coded key store. All those issues could lead to making the secure container completely useless against most of the threats. It would basically make the secure container just a layer of obfuscation. So yeah, you don't want to secure container to be like this cat keeping your secret safe. So let's talk about reverse engineering of native code. So the core of the app is rarely in native code, but it can be very interesting to look at some specific crypto function or other native codes. Although you have to know what to look for, those functions are called using the Java native interface, which enables Java code to interact with the native code. So you can use HITB, which is a great tool to reading ARM and thumb code and help you to find issues more easily. So what are we looking for? We want to know what they use to encrypt the data, if they use any external libraries. Are they implementing their own code? Would there be some native code bugs? Also, they might be using some commercial libraries. That could be some open source code that you could have a look at. So documentation, if you find that, would be better than reading some native code. So let's talk about memory analysis. We are going to go through this section and determine what is available in memory and when. So here you want to specify we want to verify some scenarios. You want to be sure the data is protected when the device is locked and on. As discussed, you don't want the device to be stolen. Put in a Faraday bag to avoid remote wipe and having someone access to memory one way or another. In order to find this information, if you know what you're looking for, you can be looking for specific things such as your own password. In the memory, you can look for your password hash using several hashing algorithms, or you can be looking for any encryption key. If it's in memory, someone else couldn't find it, and you want to do that when the phone is on. You could also look for Java object types such as lists and follow pointers in memory to see if any information can be found manually using those techniques. So yeah, by obtaining the whole memory, you can find a lot of things like file descriptor and open files and network connection. So it can be very useful to do some memory analysis. So how would you do that? There are several ways to obtain a memory dump. The easiest way is when you have access to the device once you bypass the lock screen and get root access, for instance. An also good way to get the memory dump would be to simply use the proc file system on Linux. That would show all the process as files, but it's not very accurate, and using a tool such as memfetch or recompile for RAM would be way better. Although the Dalvik VM made it easier. It can generate a memory profiling dump in response to two signals. The garbage collector can dump a hash profile, which is a heap profiler file, containing a lot of structure information. This file is stripped with Dalvik specific data, and you can read it with any Java application accepting Java hash profiles. So let's see, how do we want to read, how could you read this memory dump? A new structured way would be to just look for strings or specific data like part of keys that you know are always set that way. You could just use grep or the strings application on Linux, but you have to know that strings on the Dalvik string are UTF-16. So you would be looking for characters. So one character would be 2 bytes. The first byte would be 0 usually, zeroitized. And so this would be a way, but I mean, I personally prefer Visual VM, which is an application reading hash profiles. So you can do a lot of things with that. This is an example on the next slide where, so here we had to hide some things, but we basically do OQL query, and we will be looking for, we can do regex and look for specific strings in the memory dump. So here we can see like some SQL requests, some password, some fields named password, and some attributes that could interest us. So the next part is modifying an application. So why would you modify an application? It would help us audit an application better and see what an attacker can do. You can, for instance, auto-validate all certificates to use a proxy using like the proxy certificates. In the case the application has its own key store, you don't want to have your proxy certificate. I mean, it's too difficult to inject that. SSL could also be stripped off, and HTTP used, but the server would have to accept it. Specific could be looked for too, like lock screen bypass potentially. If they don't do it right, you could do that with modifying the application. So modifying an application would allow you to leverage the application itself to do any deobfuscation for you. Let's say they have a password hash that is very obfuscated in the file, that goes through a lot of function in the application. You can just dump it out in a log file when the application verifies the password entered. So it could save you a lot of time and shows that obfuscation is really pointless for Android applications. You could also obviously add debug logs, stack trace at specific locations. So it would be really helpful to audit application. So how would you do that? So you can decompile the application. There are some tools that make it way better, way easier for you, such as IPK tool. That would give you Smiley code. You can then modify it, recompile it with the same tool. Or you can also write Java code, compile it using Dexter, then you'd back Smiley to get it back in the Smiley format. But the application must be signed. The Android system will not install any application that is not signed. But you can self-sign the application, so since no certificate authority is needed. So let's talk about dynamic analysis. It can be very useful to understand what an application does. We are going to go through some available tools. So strace could be used to monitor system calls, track relevant input-output to network and files. It can be attached to the application process, but also trace the application from its start by hooking on the zygote process and follow the fork. This zygote process being forked when an application is started. GDB can help debug some native parts of the application. You can have a GDB remote server set up on the phone and connect to it. GTMS could be used too. It's from the Android SDK. Can generate traces. You can read with tools such as TraceView and DM TraceDump. We also have some tools that are a bit more efficient. JDB is usually used to debug Java classes. It's not really supported by the Dalvik VM. And some commands require source code and crashes are frequent, so it's not the best tool. You might want to use Java Debug Wire Protocol, JDWP, which can talk to the Java debugger and can do a lot of things. You can hook on Dalvik methods, analyze process states, etc. Unbug also, it's a very good tool using JDWP and DDMS to hook on method, and it's scriptable, so you can do a lot of things. So regarding the future of dynamic analysis on Android, some people have done some code injection, but no real practical IP is out there yet. But you can do some very interesting things with that using the Java dynamic proxy to inject bytecode on the fly. So yeah, it's great things that we could do with that. So now you know how to find vulnerabilities in secure containers and how we proceeded to test them. I'm going to give it over to Matt to conclude the talk.
Okay. Well, I'm going to kind of wrap this up, talk a little bit about what we found when actually doing testing. Biggest thing, beware of marketing claims. So some of the claims may be 100% true, but are they relevant? Again, this goes back to, so a big claim is your data is secure at rest. But if your data is never at rest, does it matter if it's secure? Personally, I don't know. I don't know if it would. To determine what secure means to you, do you need your device to be secure if a random person steals it or a random thief? Or do you need it secure from a government entity? Someone who could potentially throw, $100,000 of equipment, unlimited technical resources, and whatever they need to get your data. There's a big difference there. Ask for penetration test results, and threat models. And these companies like to tout how secure they are, and they even say they're pen tested. Why don't they release the results? Let's test it yourself. Once you have an idea of kind of where you want to be secure and how, or who you want to be secure from, test it. We just gave you, the techniques and tools you can use, more or less the exact things we did to look for issues. Go out and see if things are really as secure as they claim. Some tips for that. Watch the RAM. Insecure RAM usage can lead to many bad things. Not properly clearing things out, whatever they may be, could cause major issues. Review the crypto. Verify they have proper key usage. Also, look out for outdated crypto implementations. Are they using up-to-date standards? Are they using, something from a while ago? And again, if you think about FIPS, it just needs an improved algorithm. FIPS is kind of old. It may have approved, but it may not be the best. Also, look out for basic things like no salt or no IV. These can quickly and easily make an attacker's job that much easier. Don't rely on the Android protections to keep you safe. As we've seen, lock screen can be bypassed, and Flash can be read without debugging enabled. The UFED devices, really interesting things. They literally plug in and can make a copy of your device even if you have the screen locked and no debugging enabled, anything like that. Very interesting stuff. And finally, be careful with your sensitive data. Nothing is 100% secure. The more attack vectors there are, the harder it is to secure this. It's like your phone has so many ways into it. It's not like a laptop where you plug it in or you get on wireless, that's the way in. Your phone is constantly on some sort of wireless network, constantly exchanging data, and it's also on you all the time, everywhere you go. So easier methods to get into it and easier methods to get access to it. Again, phone has a very large threat surface. Be very careful with that. And finally, secure containers. If done right, let me restate that. Done right could be secure. Relatively. Again, we have attack vectors out there that are working at a whole nother level. Baseband exploits and firmware over the air. No matter what, these may get your data. So that's where it comes in. With those things in mind, do you really want to be carrying data that's that sensitive? Personally, I don't. So with that, we're going to close it up. I would just like to say thanks to a few people. ISEC Partners, great place. Alex Damos, he's one of the partners, been great help on this talk. Justine Osborne, she was originally supposed to be here but couldn't make it. Jesse Burns, David Teal, our actual boss, Paul Yoon, was really awesome help at the very last minute. And finally, Aaron Gratifiore. And that is it.
Well, thank you very much, ISEC Partners. Hack in the Box thanks you too for taking the time to come to Hack in the Box this year. Thank you very much.